Hello, everyone. Today we're going to be talking about permutations and the permutation groups. Um, so the first thing to do is to define a permutation. Um, so a permutation is a bijection sigma on the set of n elements. Okay. Um, so this is a permutation of n elements, right? So the set S sub n of permutations of n elements. This set S sub n is a group under composition, meaning that if we take two permutations and we compose them, we get another permutation, which is kind of obvious. The composition of two bijections is a bijection, and if we're going from 1 to n to 1 to n, and then to 1 to n again, it's the same thing as going from 1 to n to 1 to n. So, this is a very easy to see fact. Um, Now, notice that for one question we can ask is how many elements does S sub n have? How many permutations are there on n elements? Well, you probably already know this. It's just the way to rearrange n distinct objects, and that's in factorial. But let's derive that. So sigma of 1 has n choices, right? It could be 1 through n. Now notice that, right, like sigma of 1 can't equal some other sigma of j, right? Because then you wouldn't have a bijection. So everything has to be mapped to some unique number, right? So we have n choices for sigma of 1, and then sigma of 2 has n minus 1 choices, right? Because we've already chosen, sigma 2 can't be sigma 1, so that's where this minus 1 is coming from, and so on, and then you get sigma of n. Once you've chosen everything else, sigma of n is fixed. Right? There's only one possibility. So therefore, the order of S sub n is n times n minus 1 all the way down to 1, which is the factorial of n. There's a kind of, I'm forgetting the theorem, but there's a theorem that states any finite group is isomorphic to a subgroup of some S sub n. So why is that? Well, the reason is that for G in G, G essentially defines the action of multiplying every element on the left by G defines a permutation on sorry, I'm blanking out. Actually, I think think the way you want to do it is like G inverse H finds a permutation on G, and let's take sigma G1, sigma G2, H, you get sigma G1 of G2 inverse H, which is going to be G1 inverse G2 inverse H. Oh no, so, sorry. We don't have to do the inverse here. So this is showing that this does indeed define a group, right? So yeah. So in particular, we know it's a subgroup of, at most, S sub order of G, right? Okay. The next thing is cycle notation, which is sort of a way to denote certain permutation. So we denote a permutation I1 through IR to be sigma of I sub j equaling I sub j plus 1 for j equal to 1 through r minus 1. And then once you get to I sub r, you wrap back around. And sigma leaves any other element fixed. So let me give an example of this. So in S sub 4, sigma being, say, 1, 3, swaps 1 and 3, but leaves 2 and 4 fixed. Explicitly, we have sigma of 1 equals 3, sigma of 2 equals 2, sigma of 3 equals 1, and sigma of 4 equals 4. And we also have that the inverse of an element in cycle notation is given to be just the reordering, or not reordering, but just writing the cycle backwards. Okay. So now what we're going to do is, our goal is to prove that for n greater than or equal to 5, S sub n is not solvable, right? So in the last video we defined solvable groups, and we want to show that for n greater than or equal to 5, S sub n is not solvable. To do that, we need a little lemma. So let H be normal in G, then G mod H is abelian if and only if H contains all elements of the form x, y, x inverse, y inverse for x, y, and g. So right off the bat, we can see that the reason why this lemma is going to be helpful for solvability is that, remember that in solvability we have these towers of normal subgroups and the quotient groups are abelian. So this is telling us that each group in the chain in the tower is going to contain these elements. And these are called commutator elements. The reason they're called commutator elements is that this is the commutator of x and y. So this is equal to the identity if and only if x and y commute. In other words, xy equals yx, right? Because x inverse y inverse is yx inverse. So we see that this is xy times the inverse of yx. And this is only going to be equal to the identity if xy equals yx. Okay. So so let f be the natural projection, or canonical, I'll say natural projection, right, with kernel H. Okay. If G mod H is abelian, then f of xy x inverse y inverse is equal to f of x, f of y, f of x inverse f of y inverse. And since all the f of x elements, these are in G mod H, and G mod H is abelian, so we see that these cancel and then these cancel, and so we just get the identity in G mod H, or let me write it as E bar. And thus xy x inverse y inverse is contained in the kernel of f, which we know as H, right? The natural projection has a kernel of H. And therefore, we have one side of our if and only if, right? We said that if G mod H is abelian, then H will contain all of the commutator elements of G. So now conversely, let x bar, y bar be elements of G mod H. So we want to show that x bar and y bar commute. So let x bar equal f of x and y bar equal f of y, right? So x and y are coming from G. Then x bar y bar is equal to f of x, f of y. And then what we're going to do is introduce some terms here. So we're going to multiply by f of x inverse, f of y inverse, f of y, f of x. Okay, so here I've just multiplied. This is the identity, and then that cancels, and then you have the identity here. So these two things are equivalent. And now we can write this as f of xy, x inverse, y inverse, times y bar, x bar. Now this is in H, which is the kernel of f. So this is equal to E bar, y bar, x bar, and so this is equal to y bar, x bar. And so G mod H is abelian. Okay. So we showed both directions. All right, so now we can prove that, actually, we need another lemma that will essentially be the entirety of the theorem, but the lemma says that if n is a normal subgroup of H, which is a subgroup of S sub n, and H contains every 3 cycle, and h by n is abelian, then n contains every cycle. So what is a 3-cycle? By a 3-cycle, I mean that it is a cycle of 3 elements. So something like 1, 2, 3 as an element of S4, right? So 1 gets mapped to 2, 2 gets mapped to 3, 3 maps to 1, and then 4 is left the same. So that is a 3-cycle. Okay, and so essentially the idea is that we know that h by n is abelian, okay, and h contains every 3-cycle. So the goal is to show that the commutator of a 3-cycle is a 3-cycle, because we know by our lemma that if h by n is abelian, n contains every commutator of an element of elements in h. So if the commutator of 3 cycles is a 3-cycle, then n contains every 3-cycle. Oh, and I should mention here that n is greater than or equal to 5 in this case, in this lemma. Okay? And to that avail, let, what is it, I, j, so there's going to be a bunch of variables, I, j, k, r, and s be distinct integers in the set from 1 to n, right? So this set contains at least 5 distinct integers, so we can choose 5 distinct integers. Let sigma be the cycle ijk, and tau be the cycle krs. Then we want to look at what sigma, tau, sigma inverse, tau inverse is. Okay, so essentially we know that if we pass any element which isn't one of these elements, right? If we pass through any number which isn't I, j, k, r, or s, then it's going to be fixed. So this element leaves fixed for certain elements or numbers, I can't type or write today, or numbers that are not I, j, k, r, or s. So now we just need to show what happens to each of these. So sigma tau, sigma inverse, tau inverse of I. So tau leaves I fixed, so we don't have to worry about that. Now, normally sigma sends I to j, so that means the inverse is going to send I to k, right? Remember that the inverse is going to be the reverse permutation. So this is going to be sigma a tau of k. Now tau of k is r, so this is sigma of r. And sigma leaves r fixed. So I gets mapped to r. Okay? Now let's look at where j gets mapped. Okay? Again, tau leaves j fixed, so there we go. The inverse of sigma is going to send j to I. Okay. Tau leaves I fixed, so this is sigma of I. And did I do something wrong here? No, I didn't. And sigma of I is j. So this permutation leaves j fixed. Okay. Now let's look at k. All right, so k, tau sends k to r, so the inverse sends k to s. So this is sigma tau, sigma inverse of s. Sigma leaves s fixed, so this is sigma tau of s. S maps to k. S maps to k, okay, for tau, and then sigma maps k to I. So this maps k to I. Right, we're almost done. Now r, the inverse of tau will send r to k. Okay, k. The inverse of sigma will send k to j. So sigma tau of j. Now tau leaves j fixed, so this is sigma of j, and sigma sends j to k. So r gets sent to k. And now we just have to look at what happens to s. So tau inverse sends s to r. Sigma leaves r fixed. Tau sends r to s. And sigma leaves s fixed. So s and j, notice, are fixed. And thus, what we have is that sigma tau, sigma inverse, tau inverse is equal to I, R, right, I gets mapped to R gets mapped to K, and K gets mapped to I. So this is the 3-cycle IRK. Now, notice that we took 5 distinct integers. So we took 3 arbitrary, 3, not arbitrary, but essentially, since we know that H contains every 3-cycle, we know that H contains sigma and tau, and by our previous lemma, we know that N will contain sigma tau, sigma inverse, tau inverse, and so this is in N. And that concludes the lemma, right? This is an arbitrary 3-cycle, which is contained in N. So now we get our theorem, which is that S sub n for n greater than or equal to 5 is not solvable. Okay. And the proof, obviously, S sub n contains all 3 cycles. Thus, by induction on the previous lemma, a tower S sub n, which equals h sub 0 going to h sub r, must have h sub r containing all 3 cycles thus h sub r is never equal to the trivial subgroup. Right? And that concludes the proof, right? We cannot have a tower decomposition for S sub n such that we end in the trivial subgroup, because at each step, since we start with all 3 cycles, and each step we keep all the 3 cycles, that means that at h sub r, we have to have all the 3 cycles. And so, since the identity, or since the trivial subgroup doesn't contain any 3 cycles, then we're done. Okay? So yeah, that's it for this video. I hope you enjoyed, and I'll see you in the next one.